Hello, this is a tutorial of how to perform statistical tests to compare measurements between two groups of independent samples. Now, the two tests that we can use to compare two groups of independent samples are the independent samples t-test and the Mann-Whitney U-test. And this video will show you how to perform each of those tests and also how to know which one to use. Because the difference between the two is that the independent samples t-test is parametric. That means the data need to follow a normal distribution for you to be able to use it, whereas the Mann-Whitney U-test is a non-parametric version of that same thing, and you're able to use that when your data do not follow a normal distribution, so for example when you have extreme values or outliers in your data. The data set we're using for this is very simple. We have 10 people's data right here. These are their names. We don't use these for anything other than identifying the individuals. And then we also have these people's heights, the length of their feet, and we have recorded whether they are males or females. Okay, so all of these guys are men, all of these bottom ones are women. And what we are interested in finding out is whether these measurements potentially differ between the male and female subjects that we've measured in this data set. Okay, so we can have a really quick look at our variable view where I've specified some different characteristics of these variables. So for example, we have numerical data in our heights and body heights and foot lengths, which we've measured in centimeters. And then for sex, we've recorded whether the subjects were male or female. Okay, so if we go back to the data view, we can actually toggle between the label and the value for the variable sex. Okay, now in order to find out whether you use an independent samples t-test or a Mann-Whitney U-test to compare, let's say, the height of the male and female subjects in this group, you need to find out whether that variable height is normally distributed or not. And in order to do that, we need to perform a test for normality. Now that is done by going into Analyze, Descriptive Statistics, and then we go into Explore. Now what we want to do is just move body height, which is the variable that we're interested in. And we can actually test foot length at the same time, but we can't analyze them both at the same time in terms of the difference between males and females. However, we can look for both of them at the same time, whether they are normally distributed or not. Okay, so we can move both of these over into our dependent list. For now, we don't want to put anything over in here in our factor list. Now, what we want to do is we want to specify in plots that we want to produce normality plots with test. And this is where you find the tests for normality that you need to do in order to find out whether there are any significant outliers in the data, so whether the data follow a normal distribution or not. So we'll just select this one. We don't really want to produce anything else right now, except maybe a histogram might be interesting. So just deselect all of the other things and then click Continue. And then down here, you also want to specify that you only want to see whatever you've seen in plots here. You don't want all of the other gumph to go with it as well. Okay, so we'll just hit OK, and then the output of this will appear in your output file. The most important thing is this, the test for normality. Now, as you would have been explained previously, what we're looking for is the p-value for these two different tests, the Kolmogorov-Smirnov or KS and the Shapiro-Wilk. Those both essentially do the same thing, but the Shapiro-Wilk test is thought to be more reliable, especially when you have very small data sets like the one that we're analyzing now. Now, a p-value such as this, which is over 0.05, signals that actually there is no difference between the data you have and a sort of theoretical data set which is normally distributed. Okay, so that means a significant p-value in this scenario tells you that the data are normally distributed. Okay, so you don't have to worry about any outliers in this respect. So that information right here, the fact that these p-values are both over 0.05, tells you that you are able to produce an independent samples t-test to compare the measurements in these data. Okay, so that's what we're going to do. I'll go back into our data set, and in order to perform the independent samples t-test, we go into compare means, and then we want to choose the independent samples t-test, which is this one here. Now let's start with looking at body height. Okay, we put this one in here, and then for the grouping variable we use sex, because we want to compare the heights of male and female subjects. Okay, you just have to really quickly specify again that what you mean with the different groups. So just it'll ask you to go into define groups, and then just specify that group 1 is your 1, which is male, and group 2 is 2, which is female. Okay, and that's it. So you just hit OK now, and it will compare the body height of the male and female subjects in your data. This is your output right here. This is just a quick summary of what you have. You have 5 males, 5 females, the mean, standard deviations, and standard error, etc. The first part of the output right here, which is called a Levene's test for equality of variances, is just something you really quickly have to check, because in order to be able to perform an independent samples t-test, you need to know whether the variances, the sort of variation between the different groups, is equal or not. With a non-significant p-value such as this one, you can say that yes, actually there is no difference in the variances. Okay, so this is fine. You want a non-significant p-value here. However, this is what we're interested in now. If this p-value here is over 0.05, you can then look at this result right here. If this was less than 0.05, you would have to use this result, okay, where equal variances are not assumed. This right here, this p-value tells you it's less than 0.05, so that means that actually there is a significant difference in the heights of males and females in your study. Okay, so you've shown that this difference in the mean that you see here is actually a real difference. It's not due to chance, and that's the result of this test. Now, the other situation that you might come across is that actually your data do not follow a normal distribution because you have some sort of outlier in the data. And we can just really quickly manipulate our data in order to create such an outlier. So for example, let's say this person right here, for whatever reason, they have actually put the wrong height in here. Maybe they've measured it wrong, or maybe this person is just a very unusually small or short person. So let's say their height has actually been recorded as 120.9 centimeters, and we'll just give them an equivalently small foot size with that as well. So this value right here is actually now a lot smaller than all of the other values that you've recorded across this data set. Okay, so now that we have manipulated the size of this one individual in our group, we have this outlier in our data set, which is much smaller than the rest of all of the data. Let's see what that does to our test for normality, which would technically should be able to detect that there's an outlier in the data now. So we'll just repeat exactly what we did before. We'll go into descriptive statistics, explore. Everything should still be selected exactly the same that it was, but we'll just double check. Okay, normality plots with tests is selected, and we'll hit OK. And what happens now is that these values here have changed. The p-values specifically for the Shapiro-Wilk test have changed, and they're now actually significant, which means that there is a significant difference between the data that you've collected on these subjects and this hypothetical normally distributed data set. Okay, so you can't actually say anymore with confidence that your data follow a normal distribution, and that is caused entirely by this one outlier, this one really small value in the data set. And what you would do if you come across this with your results is you would have to perform a non-parametric test for differences between these groups rather than a parametric test. Okay, the non-parametric equivalent of the independent samples t-test that we've just done is the Mann-Whitney U-test. Now, in order to produce that, we'll go back into our data. We go into Analyze, Non-Parametric Tests. We go down into the Legacy Dialogues, and then choose 2 independent samples, because that hasn't changed. We're still looking at differences in 2 independent samples. Okay. Now we want to test exactly the same thing. We want to test body height, and we want to use sex as our grouping variable. We want to define our groups. Group 1 is 1, which is the males, and group 2 is 2, which is the females. Now what we want to have selected here is the Mann-Whitney-U test as an option. And we just hit OK, and our output is down here. Okay, so now we've done exactly the same thing. We've compared the body height between male and female subjects. But what the Mann-Whitney-U test does instead of the independent sampled t-test is it uses the medians and interquartile ranges in order to compare these data. Okay, so it uses ranks rather than actual averages in order to compare the heights of those subjects. It also finds that there is actually a significant difference, okay, and it's usually this asymptotic significance level, the two-tailed one, which we want to look at. This is our p-value right here. It's less than 0.05, so that means there is a significant difference in the height of those people that we measured. Okay, so that's the tests for independent samples. And if you keep watching the videos, there's a version of this where we look at exactly the same situation, but we'll actually be comparing sort of measurements between paired groups. So for example, that could be before and after we introduce some sort of treatment.